Yeah. All right, everyone. Welcome back. We're at Homeport. Next up, as a demonstration, we've got Blue Atlas Robotics. Carl, the co-founder and CTO, is going to give us a presentation on their technology and their platform. And then we're going to have a bit of a Q&A after that. So I'll hand over to Carl now. Take it away.
So, hello, my name is Carl. I am the founder and CTO of Blue Atlas Robotics. And Blue Robotics started as a project to see what it would take to image big things underwater. So we've all seen ROV footage moving around the marine environment, going from thing to thing, but it's difficult to get a large-scale picture of some of these things underwater, especially if you're operating in a low-visibility environment, such as a port or a northern sea environment that's not quite like the Mediterranean. So we built a robot, and this robot is covered with cameras from top to bottom. And the reason we did that is because if you want to see a lot underwater, the first thing you need to do is guarantee that you have a wide field of view. So this robot can see top to bottom 150 degrees. It also has a neutral point of buoyancy and center of mass, which means it's also able to angle under or below a surface, such as the bottom of a ship hull, for example. But that's not enough. In order to efficiently image something, you can't have a human operator precisely controlling an ROV for hours on end. So we've worked a lot on automating this drone through computer vision, such that it's actually able to build a map of its surroundings and environment as it operates. And it can use that 3D map to identify the general structure of what it's looking at and navigate. So this robot is capable of, by itself, with very minimal human assistance, of flying a lawnmower type inspection pattern. So we can very efficiently collect underwater data at a rate of about 1,000 square meters per hour. But once you have that, you have hours and hours of video, and remember, everything's multiplied by 6 now. So you need a way to understand that information. And of course, what we do is we process all that very stable, efficiently collected imagery into a 3D model. So this is an example of a port structure. We can see plenty of information, the different anodes, the welding structure that mounts that anodes. We can also see a lot of information that's only available in the visual spectrum. For example, the color of the soil sediment at the bottom of the quay wall. This can, of course, be an indication that there may be soil leakages from behind the wall, which is, well, it's firstly dangerous, but it's also very difficult to connect, unless you're able to see it in the visual spectrum. We're also very interested in being able to comprehensively inspect a ship hull from close distances. So that's, in our speak, that's about 50 centimeters away. So our system, it does work in the visual spectrum. It does require at least 50 centimeters of visibility. But if we have that, because we're able to efficiently scan these objects, we can stitch them back into these 3D models. This behind me, it shows the structure of a ship hull. We're still working to be able to get that comprehensive image all the way underneath, around the front, the niche areas, the propellers, but we're definitely getting much closer. So that's an introduction to what our technology can do. I'm going to leave a video playing that shows some of us deploying the images, the type of imagery that our robots are capable of collecting. And I'm going to jump into a question and answer session that hopefully we can cover some of the more interesting points. Oops. I'm a geek, so it looks a little different.
Do you want to talk us through the video as it's playing?
Okay, I'll just give a brief introduction to this. So this is typical imagery that our robots are able to collect. And on one side, we have the live video streams. On the other side, we have some of the information that the robot itself is using to navigate. So as it's moving around, it's building up that 3D map of its environment that's useful for the robot to navigate. It uses that to fit a surface, and therefore the robot's able to take over all the navigation by itself, basically. So that's what this is behind me. It's a lot of the same things, so I think it's maybe an idea to jump into some questions.
Sure. All right, Carl, so thanks for the presentation. I'm wondering where you're showing that video, and you know it's showing the imagery that's coming in direct. What about visibility in the water? I mean, is there a limitation in terms of if the water's really murky or it's deeper? I mean, how much light is required to get good imagery?
So this is Svendborg. It's very close to where we are based in Denmark, in Odense. This is nice imagery. This was done on a day with maybe 2 meters of visibility. It's not quite Mediterranean islands, but it's certainly good enough for our system to work and produce a very good 3D model. Our system is able to operate in 50 centimeters of visibility. And we've done experiments in areas where we'll do a 50 centimeter inspection and get very usable results. But if we move back to 80 centimeters even, the visibility has completely dropped off. We've also taken into consideration the lighting that our robot uses. The lights are mounted in such a way that they illuminate the surfaces from the side. That helps avoid the backscatter. It makes it a little bit better in low visibility conditions. But ultimately, this is a visual inspection tool. We can operate in lower visibilities than a lot of other tools because the autonomy is able to maintain that close and consistent distance. But once you go below that 50, 30 centimeter visibility, it becomes not the right tool for the job, I suppose.
Okay, so to follow on to that question, maybe are you able to talk us through the hardware a little bit? If we put the robot on the floor, and I think the camera will be able to at least see in general detail. Great. Oops. There we go.
So it is it's an underwater ROV. It has an unusual form factor. This is something that weighs 16 kilograms. It can be easily deployed by a person, and it's designed to be hydrodynamic for moving in a sideways direction, so we can do that underwater scanning. We do have that top-to-bottom camera arrangement. We have the lights on the side, which are protected a little bit by the frame and therefore don't produce as much backscatter in front of the cameras. It has an onboard battery. There's also a topside power solution available. But other than that, even though it looks a little bit weird, it's not so different from any other ROV, a small size ROV that might be used as a tool in a port. The real smarts take over when the smarts on board and the software start assisting the user to efficiently collect that underwater data.
Okay, and I can see a tether here. This is for power or transmitting data, or it's just to keep hold of the robot?
Yeah. So this is a data tether. We're able to stream all the high-definition video streams to the surface in real time. We also have that 3D point cloud, which is displayed to the user and is very helpful for understanding what the greater surroundings of the robot are, especially when the robot itself is pressed right up against the inspection surface. We also have these navigation cameras which point left and right, also to help the user understand their surroundings. But that is a data tether. We have visions that maybe this will be a fully autonomous robot one day, but for now it's a lot easier to pull it out of the water with a tether. Let's leave it at that.
Fair enough. Now, I'm wondering, in terms of the actual use case, I mean, is this a service provider model, sorry? Are you providing a service to the ports or maybe to ships, or will port authorities basically buy this as hardware and use it themselves?
Yeah. So we as a company, our core is technology, and we do see ourselves as a technology provider. At the same time, we realize we're bringing something new into the world, and we do think that we will be performing the additional services to the port customers or the vessel customers. In the future, we'd be likely to work through service providers that are existing around the world, but we've also fielded inquiries of people who just want this robot as a tool to go and check something quickly by themselves without having to order an external service provider to come and collect the data in a traditional way. So there are people that are expressing interest in operating this robot themselves, but currently we're looking at providing the services directly until we're able to put this into other people's hands.
Okay, and can you talk us through a bit about how Blue Atlas Robotics started and maybe how this came into being?
So this once upon a time was a bedroom project. My background is robotics. I've worked in Silicon Valley for 4 years, always at startups. I was into scuba diving, and I wanted to do the most technically challenging thing I could think of, which was to make an autonomous underwater robot. That's the worst way to start a business. Find a value proposition first, but it wasn't too hard to find one. And when we went out and started raising money, it was clear that there was a lot to be improved on ship inspections, both in terms of the quality of the data, the difficulty in getting that data, and the comprehensiveness of those inspections. So instead of looking at point inspections and trying to understand, is this part okay, is this part okay, is this part okay, we wanted to give maritime service professionals, such as technical superintendents of ships, the complete picture of their vessels. So, for example, if they're negotiating a dry dock contract, they can negotiate the services they need more precisely. They can make sure they don't miss anything. We also saw that this was a tool that could be used in a lot more environments than traditional methods. So divers are more and more not allowed to operate in ports around the world. So we do need tools to replace those services that are no longer available. Inspections are usually only taken in waters with very good visibility. That's a problem in the Nordic waters. If this tool can save a ship from needing to sail somewhere with better visibility, and we can do the inspections on site, that saves the ship owner both a lot of money, but there's also fuel savings in that as well as everything else.
Great. I will ask if there's any questions from the audience. So just put your hand up if there are, but we'll carry on a little bit as well. So I'm wondering how deep can this go? And in terms of applications, I mean, I'm a diver myself as well. You know, could you use it for broader surveys that aren't linked necessarily to shipyards or ports?
So this is going to be certified to 100 meters. The environments we tend to work in are never deeper than 20, 25 meters. So going super deep is not a huge concern of ours, but by far the most fun inquiries are the people that come out and say they're trying to monitor some coral reef life and the camera systems they have don't look in enough angles to see all the different life that's going on between the reefs. And there are a lot of potential applications out there. We are a startup. We do have to maintain focus. But I really hope we can do some of those more out there use cases for different people one day.
Great. And maybe just the last few questions from my side at least. In terms of comparing your hardware to other hardware that is out there, what's the added value or the USP?
Yeah. So a lot of people are talking about 3D twins of maritime assets because it is a good idea. The one thing that we've focused on that we haven't seen so much in the competitive space is getting the autonomy to work very reliably. And we've had this robot operating for hours with no interruptions, collecting data very efficiently, and we come back with those hours and hours and hours of data, and we can then post-process them. Because we're able to collect that imagery more comprehensively, to our knowledge, we are imaging the largest structures and doing these photogrammetric reconstructions. But it comes down to just making this a tool that's easy to use, that can be incorporated into whatever operations that it's needed for. It's easy to put in the water, it's easy to take out of the water, and when it's in the water, it can do a lot of the work itself. So you don't have to be a 10,000-hour ROV pilot. And that's our angle, to make this as easy and useful to use to as many people as possible.
Great. And how far along on that journey are you? I mean, how widely has this been deployed? Have you got new deployments in the pipeline? Yeah, talk us through that side of things.
So we are very happy with this form factor of the robot. It's been performing very well. And we are in the early stages of designing the production setup to sell these to certain niche customers. In terms of operating the robot, we've been fielding inquiries for quay walls between 1 and 2.5 kilometers. That's a lot more than we've imaged today. So we're really stretching our operational capabilities in being able to not just be efficient while the robot's in the water, but also efficient throughout the working day, throughout multiple days if necessary, and being efficient on the data processing and delivery side. But the robot itself is in its form factor that we're happy with, and if the use case is more about just doing the inspection and seeing the live video streams, we're already able to engage with certain customers.
Fantastic. So I think that's most of the questions I had here. Are there any other questions from the audience right now? I don't think so. I think you're so comprehensive. There's nothing possible to add. Would you like to wrap up with a few final comments?
Yep. Obviously, we're always very interested to talk to anyone who needs to see something underwater and is having difficulty doing it with their tools today for whatever reason. My email address is carl@Blue Atlas Robotics. Our website is also blueatlasrobotics.com, and if you're able to reach out through that, we will be more than happy to talk to you. So yeah, thank you for today.
Yeah, great. Thanks, Carl. So just a reminder, Blue Atlas Robotics will be here for the rest of the week. You have a stand somewhere, right?
Yes, we're downstairs in the container.
Okay, so if you come to the home port, you'll be able to find them at the stand. And I think you will also be presenting again a couple of times, right?
I believe so.
Yep.
Don't hold me to the schedule.
Okay, all right. So with that, we'll wrap up this session. Next up, we've got Volocopter, I think starting at 2 o'clock. So we'll draw the session to a close. So thank you very much, everyone, and thank you, Carl.
Yep. Thank you very much.
As the world becomes increasingly digitalized, so are ports and maritime transport. Sensor data collection is increasing safety and security measures and operational efficiency, whilst technologies will continue to reduce accidents, economic costs, and carbon emissions. The Robotic Vessels as a Service, aka RoboVAS project, is about demonstrating services that connect cloud-based software infrastructure, a fleet of autonomous vehicles, and innovative sensor and inspection technologies to show the potential of on-demand maritime robotic services for larger-scale deployment. When a user requests a service via the RoboVAS cloud, autonomous surface vehicles, ASV, are deployed to collect data for the given service that is relayed back to the cloud. Possible users include ship captains for anti-grounding, ship owners for hull inspection, port authorities for key wall inspections, or terminal owners for data collection. The RoboVAS demos include 5 services that provide data to the users. Ship hull inspections using the remotely operated vehicle, ROV, launched from the ASV, can inspect and locate possible damages precisely without any risking diving operations. Key wall inspections can be performed by both ASV and ROV as routine inspections with high detail sensors, thus reducing the operational costs dramatically. Data muling relies on underwater acoustic communication to transmit data, which is useful in port areas where buoys or tethers can be obstacles to vessels. Bathymetry data collection uses ASV to map depth deviation from nautical charts, allowing for up-to-date information in areas with high tidal variation. Anti-grounding has an ASV traveling ahead of a vessel and collecting depth data in real time. Depth deviation from nautical charts are communicated to the merchant vessel immediately, improving safe passage in critical areas. The RoboVAS project provides proof of concept for improving the operational flexibility of systems with unmanned underwater and surface vehicles, as well as cutting-edge sensor imagery. However, the human dimension will remain necessary, particularly for more distant operations and for safety precautions. The future system includes upgraded vehicles with improved autonomy, better underwater inspection sensor technology, and a completely new field of aerial inspection with ASV drone integration. The RoboVAS Data Cloud Network is a solid foundation to build upon for future developments. RoboVAS is a solution for on-demand shipping services and near-shore operations for all ports, offering easy accessibility to European waters and enhancing maritime transport. RoboVAS is the future of maritime port operations.
Yeah, good afternoon here from the HBA Homeport today for our demonstration of the RoboVAS project, a small demonstration. My name is Vincent Schneider. I'm the project coordinator from Fraunhofer CML, and we want to present to you today a bit what we did for the Port of the Future and kind of services that we can present with robotic VSSs. So we developed within the project this ASV, an autonomous surface vehicle, or CML. That's the first iteration. And within the project, we realized that the 5 services that we developed, which are an anti-grounding service, a key wall and ship hull inspection, bathymetry data collection, and data muling, can be experimentally shown with this vehicle, but we wanted to take it one step further. So we developed the second iteration of it, the Sea Lion, and that you will see today in a minute. So as I just said, the 5 services that we developed for the Port of the Future we not only created the services and tested them with the robots. The ASV actually can carry a small remotely operated vehicle, an ROV, and this is equipped with the camera and can be also equipped with state-of-the-art sensor technology, which we will see in a minute. All these 5 services with the vehicles together, we integrated with the web UI that can actually bring the service architecture and infrastructure right to the end user. And all this system that we integrated between the software architecture and the robots needs a profound and robust network architecture. And now my colleague Filippo Campagnaro will take over and say something about this.
Thank you, Vincent. Hello, everyone. So I am Filippo Campagnaro from the University of Padua. In order to enable the communication with the unmanned surface vehicles, we had to use long-range radio antennas, while to coordinate the mission of the vehicles that were moving underwater, radio do not work. So we had to use acoustic modems like this one, developed by the Technical University of Hamburg, as acoustic sounds waves can propagate under the sea. Now, I let Dr. Gerard Dooley from the University of Munich speaking a little bit about the sensor we used during the project.
So, good evening. So, for the infrastructure inspection subsea, we use a remotely operated vehicle, which we operate from the topside. On this vehicle, we mount very high resolution sensors for imaging. These are the imaging sensors here. These are built by Kraken Robotics in Germany. And what we do here is we distribute lasers, and we image the lasers with a high resolution camera. And from this imagery, we can denote bathymetry. And from the bathymetry, then it gives us a 3D profile of the infrastructure that we're imaging. So we get very high detailed 3D images and scans of the infrastructure. So in terms of infrastructure, what we developed this for was both ship hull infrastructure inspection and also key wall inspections. So the camera equipment here and the lasers allow us to get sub-millimeter resolution accuracies in these 3D scans. So using this, we can manage the infrastructure within the port harbour area, and we can deliver this to the customer. In terms of remotely operated vehicles, then, I'll just show you here. If you can get the screen there. So this is our ROV. That's difficult there. See this? So the ROV system, as my colleague said, radio antennas don't work underwater, and GPS systems also don't work. So we developed an ROV, which is based on an absolute positioning system, using an inertial navigation system, which gives us dead reckoning once we dive underwater. So we use accelerometers and laser systems to estimate the position of the ROV as we move through the water column. And then using this positioning information, then we developed a control system around this, and also an ROV around that. So the ROV weighs about 150 kilograms, and we deploy this then from an ASV from the surface. On the ROV, then we mount a laser imaging system. So the ROV can automatically navigate and control itself subsea next to the infrastructure, so we can maintain a good distance to the platform that we need to image, whether it's a ship's hull or it's a quay wall. And then using this control, we move then in a particular manner, doing waypoint following to image the area that we need to image. So this is an example of one of the 3D reconstructions that we did during a base camp in Ireland. So I'm not sure, does that come through okay? But you can see the resolutions there of the dock wall, that we can get sub-millimeter resolution. And then we can deliver these 3D models to the customer. So that's effectively it from the ROV systems and the imaging systems. And then I can pass you back to Vincent.
Yeah, thank you very much, Joe. And I just heard that the tanker has passed and we can start with the live demonstration. So now we see the Sea Lion in action just here in the home port. So as I just said, that's our second generation vehicle. This is 2.2 meters long by 1.50 meters and can carry up to 120 kilograms of payload. The top speed can be achieved up to 8 knots. And now if a customer has booked the service within the RoboVAR system, the vehicle starts to deploy. So today we show you how a key wall inspection can look like. So imagine the customer has just booked such an inspection, for example, the respective department of the HPA, which is also involved within this project. The vehicle is deployed and will automatically move towards the key wall that needs to be inspected. So right now you see that the key wall was very near and we could easily reach it. And the autopilot will now enter the loiter mode. And you will see that the vehicle will now position itself in the correct position towards the key wall. And once the parameters are reached and the loitering mode is satisfactory, the deployment of the ROV will start. So the ROV that we have here is a BlueROV, which is 11 kilos in weight and has a HD camera integrated, which we can use for visual inspection. But today we will only show you the launch and recovery of the system. Due to the turbidity in Hamburg, the visibility is restricted to 20 centimeters. So we will just launch the vehicle and recover it then, to show that the complete service pipeline can be shown. Once the top position is reached, the A-frame, which acts as a crane, starts deployment, as you can see now, and the ROV is lowered behind the ASV. Once the outmost position is reached, the ROV will be lowered into the water. And you can see now that the autopilot has to fight the current within the channel to keep the correct position. Now the ROV is dropped into the water, and then the inspection would start. So if we imagine a bigger ROV than the BlueROV, we can actually integrate the sensor, as we just seen, the C-Vision system. The laser technology allows further reach in the water quality that we have here in Hamburg. And we could inspect the key wall easier. But this system that we're seeing right now is our small-scale demonstration platform. So we showed the whole service pipeline here, and the C-Vision sensors is too high for the payload of the BlueROV, so we separated this within the project into a small-scale and large-scale demonstration. And that way we can cover all aspects of showing the whole pipeline works, but also it deploys state-of-the-art sensor technology. Now, as you can see, the BlueROV is lifted out of the water again, and the inspection has been successfully finished. We retract the A-frame, and the BlueROV will be lowered onto the surface of the Sea Lion. So once the A-frame is completely retracted, the BlueROV will be lowered onto the deck of the Sea Lion, and the successful recovery is terminated. And now the Sea Lion can return to its home port, or go to the next inspection site and perform a key wall, or for example in this configuration a ship hull inspection. And yeah, that's finished our today's short live demonstration of the project RoboVAS. If you're interested in a more detailed demonstration, please check out the YouTube stream of the ITS Congress, where you can see a 1-hour demonstration from yesterday, which we recorded. And everybody who is here at the Homeport Live, thank you for your attention. And if you have any questions, please feel free to ask us. Thank you all, thank you for my colleagues, and have a nice day.